Good evening, everyone. Thank you very much for coming this evening. Our speaker tonight is a distinguished and renowned scientist who has published numerous works across the fields of physics and mathematics, amongst others, including with Stephen Hawking on the nature of space and time. He is here tonight talking on the topic of fashion, faith and fantasy in our attempts to understand the universe, and I'm sure we're all looking forward to it as much as I am. So Roger Penrose.
Thank you very much. Well, it's a great pleasure and an honor for me to be able to address this august society. The title of this talk, I don't think you mentioned it, did you? At least, perhaps they don't have titles, these talks, do they? Okay. Oh, you did mention it, yes. Yes, you did mention it, sorry. Thank you very much, yes. Well, I put it down here so I can remember it myself. 1 second. Here we are. Probably needs a bit of focusing. I should explain that this title is a slight variation on the title of a book which I was supposed to write about 10 years ago. Well, I gave some lectures in Princeton, and it was 3 talks, and they wanted me to have a catchy title. So in a weak moment, when I should have I should have thought better of it, the idea of fashion, faith, and fantasy in the new physics of the universe occurred to me, which was a very bad idea because the various topics which I was going to illustrate by these words, fashion, faith, and fantasy, were more or less all topics that they were the world experts were in Princeton. And it was a bit rash, I think, for me to try and talk about these things. Put that down there, I think. Excuse me a moment. I don't need that one. Good. Right. I think I want to start by doing something which I have never done before, I think. I'm going to talk as though this was a philosophy talk, and philosophy people seem to take a bit out of their books and then read it. That was my experience. So I was going to do the same thing here. It's probably a bad idea, but I just thought it might illustrate the sort of point of view I have with regard to these topics here. Ideally, it would be very reasonable to assert that such influences as fashion, faith, or fantasy ought to be totally absent from the attitude of mind of those seriously dedicated to searching for the foundational underpinnings of the universe. Nature, after all, surely has no serious interest in the ephemeral whims of human fashion, nor should science be thought of as a faith, the dogmas of science being under continual scrutiny and subject to the rigors of experimental examination, to be abandoned the moment that a convincing conflict arises between those proposed dogmas and what we should find to be the actuality of nature. And fantasy is surely the province of certain areas of fiction and entertainment where it is not deemed essential that significant regard be paid to the requirements of consistency with observation or to logic or even to good common sense. Indeed, if a proposed scientific theory can be revealed as being too much influenced by the enslavement of fashion, by the unquestioning following of an experimentally unsupported faith, or by the romantic temptations of fantasy, then it is our duty to point such influences out and to steer away any who might perhaps unwittingly be subject to influences of this kind. Nevertheless, I have no desire to be entirely negative with regard to these qualities, for it can be argued that there is something of distinctly positive value in each of them. A fashionable theory, after all, is unlikely to have such status for purely sociological reasons. There must indeed be many positive qualities to hold multitudes of researchers to a highly fashionable area of study, and it is unlikely to be the mere desire to be part of a crowd that keeps such researchers so fascinated by what is likely to be an extremely difficult field of study. This very difficulty often having roots in a highly competitive nature of fashionable pursuits. As the extreme faith in some scientific dogmas that is sometimes expressed by researchers is also likely to have a powerful rationale, even where the faith is in the applicability of such ideas, applicability of such a dogma in circumstances that lie far beyond the original situations where strong observational support initially laid its foundations. But what about fantasy? Surely the very opposite of what we should be striving for in science. Yet we should be seeing that there are some key aspects of the nature of the universe that are so exceptionally odd, though not always fully recognized as such, that if we do not indulge in what may appear to be an outrageous flights of fantasy, we shall have no chance of coming to terms with what may well be an extraordinary underlying truth. So there's sort of something to be said for all these qualities, but nevertheless, I think it's worth pointing out, and maybe that the reasons that these things are being pursued may be more to do with these topics than they should be. So let me address some specific topics. I was going to illustrate each one of these qualities here by a particular theory, and I should say that this was 10 years ago, so that was the fashion of 10 years ago. Is it still the fashion today? Well, it's not perhaps quite the same as it was, but it's certainly very fashionable. And that is string theory. I should say that the topics I'm going to talk about are not small fish. These are big fish. So string theory, in fact, if you're somebody who doesn't know anything about what the theory is that people are working on to try and understand nature at its deepest levels, you might at least have heard of string theory. What about faith? Well, it's an even bigger fish, and that is quantum mechanics. Well, I should explain. Quantum mechanics, there's a big difference here. String theory has, it's a fashionable theory. It's still fashionable, not perhaps quite in the same way as it was 10 years ago, but it's still very fashionable, and it's driven by mathematics. There is almost zero, I should say actually zero, when it comes to the support that the theory has in observation. Quantum mechanics is completely different. There's an absolutely huge body of support for it. There's no question about that. I'm not saying that quantum mechanics doesn't deserve being the status it has. What I'm saying is it's quantum mechanics at all levels. Quantum mechanics certainly does apply extraordinarily well and has revolutionized science in a way that, well, things that just you couldn't explain, or even chemistry, you couldn't explain at all in terms of the classical ideas that had preceded quantum mechanics. But when quantum mechanics came along, then things started to make sense, and you could see how chemistry hangs together. Lots of other things also require quantum mechanics. The point that I want to make here is not that quantum mechanics is in any sense wrong at the level in which it is applied very usefully, but it's not something appropriate to apply at all levels. You see, people think that quantum mechanics is such a wonderful theory, confirmed, there's no experimental evidence which tells against it, that it must be true at all levels. But is it true at the level of the universe as a whole? Is it true at the level of a person? Or is it true at the level of, say, a cat? Well, we'll come back to that. Fantasy. Well, in a certain sense, the fantasy is an even bigger theory. And how can you get bigger than quantum mechanics? I mean bigger in scale. I don't mean bigger in the sense of the status that it has in physical theory. I'm talking about bigger now because it's a theory to do with the whole universe. And this, again, is, well, you could say it's fashionable, too. So one could have alternated these two. Some people say that string theory is fantasy and inflationary theory is fashion. I don't mind so much which way around it is. But I want to say that this, if you've read any popular book on cosmology, a modern book, you will it'll be taken that in the very early stages of the universe, there was this exponential expansion, which is supposed to have taken place, and it's supposed to explain all sorts of things, and supported by all sorts of evidence. I'll come back to that, because a lot of what I want to say will be in relation to this inflationary cosmology. I was a little bit more nervous about this one than the other ones, mainly because I thought I knew something about these other theories, and I didn't know much about that. It's just what I did know about it, I didn't believe. So I'll come to these questions later. Well, I'll try. I can't say a great deal, of course, about all of them, but I will say a little bit about each one. First of all, talking about fashion, let's go back in history first. There have been fashionable theories going way back, and here is one that you probably know about. This way I should have it. These are the elements. Well, Plato's day, the regular polyhedra supposed to represent the elements, and then of course they found there was another one. They had these ones, and the dodecahedron came along, and so that had to represent the the universe as a whole, or the cosmos or something. These are pictures taken from my book, The Road to Reality. I should explain there are no colors in The Road to Reality, so it's really those pictures. But I thought I'd add a little bit of color to it. So, okay. What about some other ancient theories? Of course, we don't believe this anymore. When I learned a little bit about this, I realized it wasn't quite such a sort of vague ideas. I mean, some of these polyhedra you can sort of relate to others, and you can cut them up and put them together and do things like that to build other ones out of them. And that was sort of related to how things might, you'd have transitions between different elements. So I think there's more of a theory there than just the idea that the polyhedra, I won't go into that because that's not what I want to talk about. There have been very fashionable theories. In fact, a lot more. I don't know how long the polyhedra idea lasted, but the Phlogiston theory of burning, that idea was that when something burns, it emits, I mean, which way around? I have to get right. It's sort of negative oxygen. Once we know about oxygen, we know that's what it is, basically. It's the wrong way around, because oxygen, burning is things taking up oxygen, so phlogiston things were emitting phlogiston. And lots of experiments seem to agree with this idea. It was put forward, I gather, by Joshua Becher in 1667, and it was Antoine Lavoisier in 1778 who showed that it really didn't quite make sense, because phlogiston, whatever it was, would have to have a negative mass. Of course, nowadays we're not so outraged by things like that. You might have things with negative energy or something. But nevertheless, that was regarded in those days as a good disproof. And you say, well, Antoine Lavoisier himself was also responsible for another fashionable theory, which was the idea that heat is a substance called caloric, and so on. So that, I think it was Lord Rumford who disproved that. So these ideas did last for a while and then didn't. String theory, well, it's not that new in a certain sense, because there were the ideas that particles, in some sense, were knots. This idea goes back to 1867 or so. Lord Kelvin had this idea, and Tate got very keen on it, and people started classifying knots and so on, and thinking of this as an explanation for what elementary particles were. And that isn't so different, I suppose, from modern ideas about string theory. The modern ideas of string theory are motivated basically from certain things in quantum field theory. Trouble with quantum field theory is you get infinities. It's quantum theory taken when you described quantum theory as applied to fields. And quantum field theory is very accurate if you work it right. The trouble is if you don't work it right, you get infinity. That's the trouble with it. It produces answers which make nonsense. So you have to develop a certain body of techniques which get rid of these infinities, and then if you do it all right, you amazingly get wonderful answers. However, you still have these infinities, and one idea for how you might get rid of the infinities was string theory, which is actually the initial version of string theory was something struck me as very elegant and beautiful, and I certainly was quite attracted with that. What I didn't like was the way it went afterwards, which was to introduce extra dimensions. So you probably heard about this idea that do we just live in 4 dimensions? Well, those 4 are the 3 dimensions of space together with the 1 dimension of time. But it was found that string theory led to inconsistencies in the form, certainly, that they had it, and that these inconsistencies were removed if you pretended that your space had 26 dimensions. Well, when I heard that, I more or less gave up on the idea, because obviously space doesn't have 25 dimensions and 1 time dimension. That just isn't like that. But still, that's where it was. And then people brought it down to 10 by introducing ideas of what's called supersymmetry, and now up to 11 from M theory, and then maybe F theory goes up to 12. It's not quite sure about these numbers, but that means the space part is always one less. No, in the case of F theory, it's different, but these are always one less than these numbers here. Then the question arises, why don't we see these extra dimensions? Well, the idea is, okay, well, they're all curled up into a little tiny little thing, and so you imagine a hose pipe, something like that. And if you look at it from a distance, it looks like a one-dimensional thing, but if you look at it close, you see that it really has a surface going around it, and that's what it's like. The dimension that goes around it is what they call a small dimension, and so that all the ones you see, the case of, well, let's take the 10-dimensional case, you have 9 space dimensions, so that 3 of those would be the ones that we experience, and then tied up into a little knot somehow with the other 6. Well, that's the way it was supposed to work, but I don't want to go into the details of this, but I never was very happy with this because it seemed to me there were mathematical problems with even if you can't see the dimensions, the fact that they're there potentially means that you have an incredible amount of freedom in fields which you don't ever see. And there's supposed to be some explanation that it would take too much energy to excite these extra degrees of freedom, and that this is something which you can't do if it's that small. It's very difficult to excite these things. But for various reasons, I find that totally unconvincing. I don't think I'll go into that here because it's a little bit too technical, but I just thought I would give you some impression of what string theory is like, and partly why I'm not happy with it. It's not the string theory I don't like. I think it's actually a rather nice idea, an attractive idea, could be right. But what I don't like is having to go up to extra dimensions, because I think that the freedom that you have to suppress all those extra degrees of freedoms, and it just doesn't make sense to me that you can keep them under control. It's a topic which is not normally discussed very much, but it's, I think, recognized that there is this problem. When I was writing my book, The Road to Reality, which I drew all the diagrams for, I had more fun, I think, drawing the diagrams for string theory because I hadn't the remotest idea what they actually looked like, you see. There are these things called D-branes, which are part of the whole theory, and I had no idea what a D-brane would look like, so how do you draw it? So it just means I had complete freedom, drawing it any way I like. And these are strings, you see, it's supposed to have their ends attached to the D-brane. And then you might be a part of that D-brane, you see. A being would be that. I don't want to go into the strings really any more than that, just to say that I think the strength of string theory is very much in the mathematics, that the ideas spill over into mathematics and have had a very big influence on mathematics as in different areas of mathematics, which have been influenced by string theory, and that's fine. I have nothing against that. It's just that it's not clear that it has a great deal to do with physics. Well, I mean, it could do, but the extra dimensions, it seems to me, are a great problem. Okay, well, let's move on then to the faith. And I want to say something about quantum mechanics and why I think that quantum mechanics, okay, it works extremely well, but it's not the right answer. It's a partial answer to something. It's an approximation to something. Let's try and say something about quantum theory. Well, I think I'll illustrate it with this picture here. You might say, what on earth has that got to do with quantum theory? Well, I had a book earlier which was called The Emperor's New Mind, based on it's a play. The title is a play on the idea, of course, in The Emperor's New Clothes by Hans Christian Andersen. And I was rather surprised to be invited to give a talk to the Hans Christian Andersen Society on something or other. And I thought, well, I don't want to use the Emperor's New Mind because I'm the Emperor's New Clothes, but I thought I'd try and think of another Hans Christian Andersen story and see if I could relate that to what I was interested in at the time. The date, I think, is down here somewhere, if I can see it. It's not, actually. But it was in the early 2000s, 2002 or something like that. And it was just coming up to the anniversary, the centenary of Hans Christian Andersen. And so they were having a bit of a thing about him. And so I realized that the story of the mermaid might be a useful thing to illustrate quantum mechanics. So here we have the mermaid, and there's the prince over there she's looking at. And you say, what's that got to do with quantum mechanics? Well, the idea is that this picture represents two parts of physics. And you have above the water classical physics. So that's the classical world. And underneath the water, we have the quantum world. And the classical world has these separate objects sitting out there, people and things walking around, and buildings and so on. And the quantum world is this entangled build. That's one of the things about quantum mechanics, because everything's all entangled with each other in a strange way. And so you see that's represented by this sea of entanglements with seaweed and strange fish and animals and things like that underneath. So there's the strange world, quantum world, and the classical world. And the mermaid herself is the connection between the two. And she's both, you see. She's both inhabits the sea, and that's the quantum world part, and the classical world. She also played a different role in the story, which I won't go into here, but the point is that this picture had to do with the two roles of quantum mechanics. I better say something a bit more about that, and actually say something a little serious about quantum mechanics. So this is quantum mechanics, more or less, on this slide. So we have, if you like, two basic experiments. These are meant to be idealized experiments, but they're real experiments as well. You have here a source of, well, this is a photon coming along, a quantum entity, whether it's a wave or a particle is a question. And in this first experiment, you have a mirror sitting here, which is what's called half-silvered, or more technically, it's what's called a beam splitter, which means that half the light goes through it and half the light is reflected. And if you have detectors here and here, each time a photon goes along, either it's reflected or it's transmitted. And you find that either this detector will receive the photon or this one will. You never get them both at once. It's never the case that neither of them registers. So that you have an exclusive or, this thing. Either this or this, not both, not neither. And that's a particle-like behavior. It either goes this way or it goes this way. But then you can do the following. You have a half-silvered or a beam splitter here, two real mirrors there, another half-silvered one there. And then what you find, you put two detectors, one here and here, and you see the photon could do all sorts of things. It could go this way, this way, this way, this way, this way, this way, this, and 4 different things it could do. And you say, well, suppose this one, if it was like a particle, it could go this way or this way, and when it comes here, this one could go that way, this one could go this way, this way. But what you find, and let's suppose that all these path lengths are equal, what you would find is this is always this detector receives the photon, never that one. And that's completely unlike a particle behavior, but it is like what it would be if this was just a little wave. You see, a little wave comes along, and then it gets either reinforces and it goes this way, it cancels itself out, and that's the other way. So you find it always comes this way. But then that explanation doesn't work over here. So you find, you see, at the beam splitter, it's split into 2 bits, and then you find why, this case, why doesn't it work? So you can't find one explanation of a classical type, either a little particle or a little wave, which works for both. So somehow it's a mysterious thing which, well, the way we understand it, understanding is perhaps a little bit of an overstatement here, but the way we do it in quantum mechanics is to say that the two alternatives, and let's think of alternative A as going this way and alternative B is that way. These two alternatives somehow coexist. The thing doesn't know which it's done, or in a sense it's done them both at once. They both have to contribute to the final result. So possibility A, that's going this way, and possibility B, going that way, both simultaneously take place in some strange way. And then you have these funny weighting coefficients here, which I call W and Z. And you might think they were probabilities of one thing or the other happening, but they're not, because these numbers turn out to be complex numbers. A complex number involves the square root of -1, and here we have a role for these funny numbers, which seem like mathematical inventions, and suddenly you see there they are, sitting there in the basis of physical action. You can plot these numbers in a plane where this the multiples of the square root of -1 now go this way and the real part's that way. And so it's a point on the plane. That's a usual way of representing these complex numbers. And then you have the two processes. Now go back to my picture here. You see the classical and the quantum world. The things I'm calling U, I have the letter U to represent what's called unitary evolution. That is the quantum activity there. And the process R, that's the other part of quantum mechanics, is what the mermaid is doing. She's somehow, well, let me just say, suppose you have a quantum system, which might be, say, a particle, and you've got a detector, say a Geiger counter. And that detector might click when it receives the particle. Now, what that's done is to convert this quantum level thing, which is the particle, into a classical level thing, which is the click. So you hear it, and either you hear it or you don't. And that's supposed to be something which is big enough to be classical, so the idea goes. So the mermaid is playing the role of this detection device. So the Geiger counter is like a detection device, and she's playing the role of the detection device, which is somehow measuring the quantum thing and dragging it up to the classical level. And that's, I'm using the word R for that. C means classical level, U means the quantum level, unitary evolution, that is. And R is the reduction of the state, or the collapse of the wave function, as it's called, which is this process down here. And then you have these things do become probabilities. You have to take the points, see where they are in the picture, and you see how far away they are from the origin. You square those, and then you take the ratio of them. I'm not going to talk about the details of this, but that's the basic idea, is that you have two completely different processes in quantum mechanics. This one, the evolution, which turns out to be like in classical mechanics, you have a completely deterministic evolution. The thing just goes along according to the equations. There are no probabilities. It just carries on. And then there's the measurement thing, which is suddenly you get probabilities. Now, how do you understand that? This is the sort of thing called the measurement paradox, or the measurement problem, it's usually called. I think it should really be called the paradox, because it is a paradox. Because it's all very well to say, well, what you do is when you've got a detector, you suddenly use the R procedure instead of using the U procedure. But who's to say what a measuring apparatus really is? Because it's only made out of electrons and protons and goodness knows what, the same quantum ingredients as everything else is. So why should you suddenly change the rules just because you've called it a detector, or just because it's magnified the effects up to a bigger level? So that's the question. And the real problem here is a particular feature of U, which is what's called linear. Now, what does that mean? It means the evolution of A, you see that does something. It just chugs along according to the equations. B chugs along according to the equations, and it's completely deterministic what it does. And linear means that if you have one of these superpositions of the two things, they each chug along themselves in the same way as they would individually, and that superposition just continues like that. I'll give you an example of this here. Here we have, well, just put it like this. Here we have A, one thing that might happen. It's like the A I just had up in the picture. Suppose you have a laser, photon coming along, hits a green thing, produces a lot of stuff. Or you might put a mirror in the way, hits the brown thing and hits a lot of stuff. Or you might put a beam splitter in the way, and then it has to do, see, this thing is superposed between that, and because it's linear, everything that happens afterwards has to be superposed also between this and this. So it's this linearity which means that you get these superpositions carrying right through like this. Okay, so what does Schrödinger have to say about this? Well, what does Schrödinger say? Well, one thing, he said lots of things, but one thing he said, and that's the thing people seem to know about him, is his cat. This is a slight variation on Schrödinger's cat. He had a vial of poison and all that, and he didn't have a beam splitter, he had a radioactive atom. But it's the same thing. Here I'm having a lethal thing, a gun here. Well, it doesn't matter what it is here. The photon comes along, activates this detector, and kills the poor cat. You see, in the mermaid story, this was the mermaid, and it was when she when the sunlight comes up and the first ray of sun hits her, you see, then she dies. And so the idea was that to try and protect the poor mermaid, you insert a mirror, and then she's saved. You see, like this. The cat is saved here. But of course, if that was a beam splitter, you know what I'm going to do, or what Schrödinger did, is you see, pretend this is a beam splitter, and then you have to consider that according to this linear progression, this Schrödinger's own equation, he was talking about his own equation. This is what his equation says would happen, is you get a cat which is dead and alive at the same time, and he was more or less saying, don't believe it, because a cat wouldn't be dead and alive at the same time. There must be something else coming in. His equation is not the end-all of quantum mechanics. That's what he was more or less saying. However, what people usually say, if I show them this, they say, oh, you've forgotten to put in the environment. There's all this air going around, and it's not as simple as that. Well, the answer to that is, okay, there's the environment. And then we have the other one. And I have to make sure I don't get messed up here, of course. Here's the other one. And there's its environment. I'm not saying you can see the difference, but there is a difference. They're in slightly different places. Well, all right, there's the answer. That's what happens. Doesn't seem to me it makes any difference. You see, what people do is they say, oh, well, we don't know what the environment is doing, so we do something else. We average over it in some clever way. Okay, but it's not really an answer. It doesn't tell you why it suddenly something, because you could imagine taking into account all those different processes there. Okay, well, somebody might say, well, no, you've forgotten to take in the account of the conscious observer coming along and looking at it. So I said, all right, let's take the conscious observer and take into consideration too. There we are, and you can put the environment on if you like. I think I won't, just because it gets rather clouded if I put too many things at once. But imagine the environment's there too. And this is the mental image that the conscious observer has. And you might not know how to treat that quantum mechanically. Well, you wouldn't know, but you don't need to know because you just look at the expression on the person's face, which is a little unhappy. And so if we put the other one, which is the live cat, and then it's accompanied by the observer, and the observer has this image of the live cat, of course, and a much happier expression. But then, of course, Schrödinger would say, according to his equation, whatever's going on here, if it is according to his equation, you've got this superposition. Let's put all the environments there too, and there you are, you see. And why is it that you don't see a cat which is half dead and half alive and all that stuff? Well, some people would say, well, there's many worlds, and there's one part of you goes into one world and another part. I don't see why that's explained by this, because it's all happening together. Okay, so that's the problem. And for a long time, it seemed to me that's just, I think Schrödinger too and Einstein, it's not as though there's this viewpoint that was unexpressed by people. It was some of the greatest scientists of the time, Einstein in particular, of course, who were not happy with quantum mechanics, and they said, well, it's not a complete answer. And I think that's true. It's not a complete answer, and the view, I would say, I'm afraid I've got this is an old slide, that should be a laser there, but it's got an old lamp instead. Never mind, it's the same thing. Instead of having a cat that's making life complicated, you could have something which either moves or it doesn't, and then you look at the space-time that moves or it doesn't, and it gets distorted, and then you have to worry about space-time structure, and that seems to me is the key issue. I don't have a theory which would address all these questions, but I have a scheme which was basically the same as a scheme that a Hungarian Lajos Diósi put forward several years before I did, but it's the same kind of idea. He had different motivations. And you can test to see whether if you have something big enough, you see a cat or something like that would be going too far. But suppose we have something like a little tiny, in the experiment which has been suggested here, it's one of many, many experiments. This particular one is under the Dick Baumeister, his name must be appearing here somewhere. Yes, there he is. In his experiment they've been doing for about 11 or 12 years now. When I last saw him, he said, we'll have an answer for you in 10 years, which I was rather surprised by, because it didn't seem to me that one could be sure about these things, but he claimed that he would have an answer to whether the scheme that we were proposing, that Stioschi and I were proposing, actually is right or not. What we say is that when gravity gets involved, and it gets involved really quite soon, that the rules change, and that you do get either one thing or the other happening. And this particular experiment involves a beam splitter. I won't go into this here, but here you have a little mirror, which is a little cube, actually. And that little cube is about 1/10 of the thickness of a human hair. So it's just too small to see, but it's just big enough that according to this scheme, it would go into one. You see, you put it into superposition, like the Schrödinger's cat. You put it into a superposition of two little different locations, which differ from each other only by about the width of an atomic nucleus. So they don't differ very much. But they're in a superposition of two places at once. And the theory says that in a certain time of about a minute or so, it ought to do one or the other. And you should be able to do an experiment to see that. Well, I have no idea. You have to wait and see. Maybe only by now, only about 8 years you have to wait. So I'm hanging in there. Okay, what about the fantasy? Now, fantasy, I was illustrating by inflationary cosmology. So let me say something about inflationary cosmology. Okay. Before I talk about inflationary cosmology, let's talk about cosmology as we understand it now. There is, the Nobel Prize for physics, not this last year, but the year before, was given for the discovery of the exponential expansion of the universe, which is illustrated in this picture. Here we have time going up. This is meant to be a space-time picture, and I can't put enough space dimensions in, of course, so I've only put one in. So you have to imagine that this dimension going this way is space, and this dimension is time. What's going around the back? Well, I've just been vague about that because it might be closed up, it might be open. Who knows what it does in the very distant regions? It's not important for what I want to say. Here we have the Big Bang. This is as time goes, you see, expansion, and then the expansion slows down a bit, and then it starts to accelerate. And that's what we're seeing now. We're somewhere up here, where we've just started to see that exponential acceleration. That exponential acceleration is explained by Einstein's modified theory. He introduced the thing called the cosmological constant, usually called lambda, which he introduced in 1917 for admittedly the wrong reasons. He wanted a universe that was static. And this was before Hubble had shown that the universe actually is expanding. And he then retracted his cosmological constant because he realized it was a mistake to want to have the universe static, because it isn't static. So he then retracted his cosmological constant. That was the mistake. He thought it was a mistake to put it in. The mistake was to retract it because we see it's there, because the cosmological constant is what's doing that expansion. Well, people call it dark energy or something like that sometimes, but it is exactly what Einstein's lambda term gives you. Okay, well, I'm accepting all that. It seems to be a perfectly good picture, explanation of what's going on. Now, what about inflation? You see, is there any inflation in this picture? Well, there might be. You can't tell because it would be tucked right into the scale I've drawn it. It would be tucked right in there and you simply wouldn't see it. So if we want to have a look at inflation, we're going to have to magnify that out and see what we get. Well, I'm afraid that's not a real magnifying glass, so let me just do it here. You may ask what that is. That's the handle of the magnifying glass. What do we see? Well, according to inflationary cosmology, you see this expansion, which was another exponential expansion, which was supposed to have been tucked in right at the beginning. So it did that, changed its mind, did something else, and then came back to its original idea. So that's the view of inflation. And in fact, the scheme of inflation does have this exponential expansion, which would match very closely the sort that we see on a far larger scale. So it's absolutely ridiculously larger scale when we're talking about the universe as a whole. But it's very similar in many ways. Okay, Now that's the thing I'm worried about. Is inflation there? Or was it there, I should have said, I suppose. Was inflation there? If it wasn't, how do you explain those things that people put it in there for? So that's a very good question. But before trying to answer that question, let me ask another question, which is, why do we believe in the Big Bang anyway? Well, there are lots of reasons. You see the galaxies going away from us and things like this. But one of the most powerful pieces of evidence for the Big Bang, I mean, when I was in Cambridge as a graduate student, the theory of the universe that was very popular at the time, particularly in Cambridge, because it were Cambridge people who had put it forward, was the steady state model of the universe. And I found this a very attractive idea. The universe was expanding, and there was new material created all the time. Very, very tenuous, very low density material, which was produced just enough to compensate for the expansion. So as it expanded, it gets more and more rarefied, but just a little bit of hydrogen came back in. That idea was a little funny, but nevertheless, it seemed to make sense for a while. But the thing which rather shot it down, the main thing which did, there were other things that did, but the main thing which shot it down was this thing called the microwave background. Now, the microwave background, another Nobel Prize, it got it twice on two separate occasions, so it's very important. It got it once for the discovery and later on for more detailed features of it. In fact, what I'm just going to show you is one of them. This is radiation coming from all directions in space, electromagnetic radiation, so it's light, but it's very, very low frequency light. And it's microwave, like a microwave oven, I suppose, microwave radiation. And it is sometimes referred to as the flash of the Big Bang, cooled down by the expansion of the universe. So it was very hot at one time, some enormously hot radiation, which then, because the universe expanded by so much, it's got down to this temperature of what is now 2.7 degrees above absolute zero. So not very hot, even colder than outside today, a lot colder. But this radiation, which was discovered accidentally, has two remarkable properties. It has lots and lots more remarkable properties, but the original remarkable properties were, first of all, I'll say, it's this spectrum here. This curve represents the frequencies of the light, of the wave, of the electromagnetic radiation, plotted this way, increasing frequencies this way, and this is the intensity this way. And here we have a curve plotted. This plotted curve is the theoretical curve which was deduced by Max Planck, and I'll say a little bit about this. This is what started off quantum mechanics. It's the Planck spectrum. And it's extremely accurately represented by the actual data. You see these things here are error bars, but the error bars are exaggerated by a factor of 500. So that means that you have to squash them down by a factor of 500, and you'll see that even the worst ones down here are all hugging this curve to within the thickness of the incline. Now, this is an old slide. I don't know, probably these days these error bars are much smaller now. But you see an incredibly precise agreement between the frequencies of this radiation and this curve calculated by Max Planck. Now, what does that tell us? What was the huge assumption that the thing that Max Planck was interested in was what's called blackbody radiation, which meant if you have matter and radiation in equilibrium, then the radiation has this curve for the intensities of various frequencies. And that particular curve was deduced by Max Planck on the basis of his quantum. He said that energy comes in little parcels. He had this formula, E equals h nu. Nu is the frequency, h is his constant, Planck's constant, and the energy is given in bulk, or the frequency and the energy are related in these little bundles of particles, which Einstein then, I'm not sure who the name photon came. It was basically Einstein who pointed out that this meant that light had to be, in some sense, made of particles. So it's particles on the one hand and light on the other hand, and waves on the other hand. But nevertheless, this particle picture was necessary to explain this curve. But the key point I'm going to say about here is that it's indicating what you get when you have thermal equilibrium. Now, what is thermal equilibrium? Thermal equilibrium means maximum entropy. Now, what is entropy? You see, entropy is basically a measure of randomness. So you say, the second law of thermodynamics says that randomness is increasing all the time. It's a very familiar law. It's telling us that this randomness is increasing. It's a depressing law, if you like. It's telling us the world is getting more and more random. It's not really as depressing as you might think. It's the law that we depend upon in many ways. But there's a sort of paradox here, because if you trace your way back, see, it's telling you that the entropy is increasing with time, randomness is increasing. And in a certain sense, that's almost obvious, you see. If you just let something go, it's going to get more and more random. But what does it also say? Go back in time, it says it's getting less and less random. So that means as you go back and back and back and back and back, till you get to the Big Bang, it must be very unrandom at that time. But what do you see? You see this curve. This is the Planck curve, which is telling you what you're looking at is thermal equilibrium, which is maximum entropy. Now, it always seemed to me that such a blatant thing as that should be worried about by cosmologists. Why don't they say, there's a big problem here. We've got to understand why you have this extraordinary contradiction, it seems, by the extreme randomness at the beginning, and it's supposed to be the most organized state that we have in the universe. It's getting more and more random as time goes on. Well, I think people thought, well, the universe is expanding, so that's what it's got to do with. Well, it doesn't work. The expansion, it was understood by people like Tolman and no one, that that's not the answer. The answer has nothing to do with the expansion, and you can see why it's not. I won't go into that here. I'll tell you what the answer is, though, because that's important. The answer has to do with the following. That's the second law of thermodynamics, and you might think of a gas in a box, and if you tuck it in one corner, you see that's rather low entropy because it's not quite so random as it should be. It's all tucked in the corner. You remove compartments there, let it spread out, and it gets more and more random. That's entropy increasing, and that's exactly what happens. Now, what was the universe like at the beginning? Well, you see, I said one thing about the blackbody radiation. It has the Planck spectrum. Another thing about it, the other key thing about it, is it's very, very uniform over the whole sky. Very, very uniform. In fact, there's slight temperature variations as you go round. You have to correct for the Earth's motion, but you do that. There's slight temperature variations. Those temperature variations are less than 1 part in 100,000. So it's very, very uniform over the whole sky. And this is consistent with high entropy. Again, you've still got the problem. But let's consider another situation. Let's suppose these are in our box. It's a huge galactic scale box. Instead, these are stars running around in the box. They attract each other gravitationally, and so they start to clump. And so you see something, even though the entropy is still going up, it looks very different from this. Here we have uniformity increasing, here we have uniformity decreasing. So as soon as you take gravity into consideration, and that's what is not being considered here because people simply assumed that the universe was very uniform. That was the assumption. If you want to solve the equations, you have to assume the universe is uniform. Otherwise, you get stuck. So that was what people did without realizing what a huge assumption that is. And you can see why it's a huge assumption, because the uniform one is a very high, I have to get my entropy right, a low entropy situation as far as gravity is concerned. So gravity says this is low entropy, everything else says this is high entropy. What you see is a combination. It's a combination between two completely different things. A very high entropy situation with the matter and a very low entropy situation as far as the gravity is concerned. And it's this curious combination, total imbalance between the matter and the gravitation, which seems to me to be the most fundamental problem in cosmology. Yet, if you look at a list of the great problems that people list in cosmology about what the main problems are, you don't see this problem. It's not mentioned. Now, so it's also vital to our existence, this. Let me just explain why it's vital to our existence. Okay. Why are we here? Well, all sorts of reasons. But one reason is we keep alive because we get energy from the sun. Is that right? Not really. Do we get energy from the sun? When I say we, I'm talking about the whole planet. Well, you see, we get heat from the sun, but in days like this, you don't feel very hot. Well, that's because it's all gone radiating back out to space. And there must be as much radiation going out as coming in, or else the Earth would simply get hotter. Well, it is getting a bit hotter through global warming, but that's a tiny effect in comparison with this. You have lots of heat coming in and just as about the same amount going out. So energy is conserved, so in fact, it's got to do that. That's not what we live on. You tend to think we need energy to live, but the key point is not the energy. The key point is we keep our entropy down. That is the crucial thing. We have to keep our organization right. If you just got energy, you just get fatter and fatter, and that's not such a good thing. You want to get useful energy out. And the key point here is that the sun is hot and the dark sky is cold. Hot means that the photons coming from the sun are higher frequency. They're yellow photons. The ones that go back to sky are low frequency. These are infrared photons. By Planck's law, E equals h nu, the energy and the frequency of a photon are proportional to each other. So that means that these high-frequency photons are individually much more energetic. That means you need many, many more of them to carry the same energy away as comes in. This is a point Schrödinger made, and a lot of people took a lot of time to understand this point. It's a key point, that the thing that we live on is this entropy imbalance, and it's the hot spot in the dark sky. You need both. If the sky was simply the same temperature as the sun all over, it would be completely useless. You have to have this imbalance between the two. Why do we get it? All sorts of complicated reasons, but the key point, when it comes down to it, is that the sun is there because of gravitational clumping. It's exactly this process of matter coming together and clumping. Okay. In this little corner here, I've got a black hole. That represents a maximum entropy state, and that means that you get these singularities. I didn't really use the word singularities before, but the Big Bang is a singularity. It's a singularity. That means that the equations that you've been using break down. They go wrong. Things go to infinity. And here we have our original picture of the universe, if you like. And here we have the singularity where the equations go wrong and somehow magic or something happens here, or who knows what. You've got some theory which explains singularities. But it's not the only singularity, because you've got the ones in black holes too. So the key difference is the entropy is very high in the black hole singularities and very low in that one. And the big puzzle is, why were the gravitational degrees of freedom not activated in the early universe? And inflation doesn't make any mark on that at all. It does other things, but it doesn't do that. And you can easily see why it doesn't, because you could imagine that the universe was collapsing. There it is, collapsing. Now, if the universe was you see, entropy is going up this way. But let's suppose that the universe was more or less the same as it is, but with the time going the other way. But you jiggle everything just a little bit so that the entropy still goes up as you go this way. Well, it's still collapsing, and the entropy can go up, but you don't get a nice little... Have I got this the right way up? I think we have now. Yes, here we are. You don't get a nice singularity without gravitational degrees of freedom activated like the Big Bang, low entropy. You get an enormously high entropy because all the black holes mix up together, and that's a great mess. And that's the great mess that you would get for a collapsing universe with entropy increasing. Problem is, why didn't we start that way? Why did we start that way and not this way? Inflation doesn't help, because you can put your equations of inflation in here just as well, and it simply doesn't get you out of it. So I was never happy with inflation. That's the reason I wasn't happy with inflation, basically, in a few pictures. But then what's the real answer? Well, you see, I did say in my beginning introduction that there are pretty odd things going on in the universe, and they need odd explanations. So maybe a bit of fantasy isn't such a bad idea. Now, I regard inflation as one bit of fantasy, and in my view, that's what it is. it does explain certain things. If it's not right, you need another theory which would explain those things too. So I'm going to give you my bit of fantasy. And my bit of fantasy is the following. Here we have the original picture I had on a smaller scale. There's the Big Bang, there's the exponential expansion that got the Nobel Prize. Big Bang got the Nobel Prize twice. 2 Nobel Prizes here and 1 here. Now, I'm going to do 2 tricks. These are purely mathematical tricks, and I've been playing with these tricks for decades. One of them is to discuss infinity. It's quite useful. What you do is you squash it down until it's a nice finite boundary. And you do it in a very nice mathematical way, which is called a conformal map. So you squash and stretch in a way which does least harm to the physics. In fact, it does no harm whatsoever to lots of parts of physics. Maxwell's equations, for instance, the beautiful equations which govern the behavior of light, electricity and magnetism and light, are invariant under this squashing and stretching. Most of physics is actually invariant under squashing and stretching. The only things that aren't, apparently, are things to do with mass. So if you don't have things to do with mass, it seems the universe doesn't know how big it is. What determines the scale is whether you've got mass. Now, when you go right back to the beginning, you can apply another trick. This is really due to my colleague Paul Todd in Oxford. And his trick was not to try and explain anything really in physics, but just to have a nice way of representing the conditions that you have on the initial state, which would agree with what we see of the universe. And that's a mathematical way of doing it, nice and pretty. What you do is you do this stretch, like this squash, but the opposite way around. So it's this conformal stretch. And if you can do that and have a nice smooth beginning, that means that you have a universe which looks like ours with very, very low entropy in the gravitational field. Now, okay, so there is a hypothesis that you can do that. This one more or less comes automatically. The fact that you can do this squash, okay. However, there's another hypothesis. See, that's mathematics. You can draw it that way. But the physics also is quite happy with this, maybe. It's happy with it with this part because I said mass is the problem. Now, what happens when you go way, way back into the Big Bang? The temperatures go up and up and up and up until you get to a temperature which is at the sort of energies that people are doing at the LHC, that kind of energy, where they claim maybe they have found what's called the Higgs particle. The Higgs particle is supposed to be responsible, in a sense, for the mass of all other particles. Now, that's exactly how you say that. I'm not quite sure the right way to say it, but it's if you go to higher energies than the Higgs, then particles are in effect massless. So the mass is gone if you go to higher energies. So if you go back earlier than the Higgs temperature, where the Higgs particle comes in, so the temperatures get higher and higher than that, then it's in effect nothing has mass. So these particles that don't have any mass don't know this from this. As far as they're concerned, this is just the universe is carrying on, and it might have had somewhere down there. I'm going to put a converse hypothesis here. Now, this is unconventional, to say that there is a sort of inverse Higgs process, which takes place when the temperature gets extremely low, and then mass fades out. Particles, the mass fades away. Now, that is a hypothesis. There is no observational evidence against it. There's no observational evidence in favor of it. Well, it could be that if the scheme works, that would be evidence for that. But what is the scheme? The scheme is that this universe that I've been talking about is, I claim, just one eon. I looked up the word eon in the dictionary to make sure it wasn't a definite number of years, and it doesn't seem to be. So I'm regarding the entire history of our universe, as we think of it, is just, I'm calling it an eon now. The universe is this succession of eons, one after the other, where there was an eon before ours, and its infinity, squashed down, is the same as our Big Bang stretched out. Or I should say, we are the continuation of this one. And that the physics, since no mass is around, just around here, hanging around these junctions, mass is sort of faded away, and then it comes back again. So it fades out and comes back again. And when it's faded out, you can have a nice join between these two things. Now, this is an outrageous idea. And when I talked about this, I lectured on this, and I called it an outrageous idea. I wanted to get in there first. You see, somebody said, look, this is an outrageous idea. Yes, that's what I said. It's an outrageous idea. But then, you see, after a while, I got used to the idea, and I just call it a theory or something like that. And I think this is the... Well, I'm going to tell you a little bit of a story about this. You see, it doesn't agree with the inflation. If you had inflation as well as this, you'd been in trouble for various reasons. But you could have it as a replacement for inflation. I said that inflation was as though tucked in near the Big Bang was this another one of these exponential expansions. What I'm saying is, yes, there was one, but it was before the Big Bang. Now, that idea wasn't original with me either. There was an Italian physicist, a very distinguished one. In fact, he was one of the people who originated string theory right at the beginning, called Veneziano. And he had an idea also, which is very much like this. It wasn't developed to the extent that this one is, but it was to some extent like this. And he was arguing that, in a sense, the inflationary phase wasn't after the Big Bang, it was before the Big Bang. And that's what I'm saying too. Okay, is this just fantasy? Can one see any evidence for it? Well, it did seem to me that you should be able to see evidence for it. And this comes about, well, I was just trying to think, what on earth could be a signal that gets to us from the eon prior to ours? I tried to think of the most violent thing that I could imagine. And the most violent thing that I can imagine is the collision between two supermassive black holes. Now, our galaxy has a black hole in its center of about 4 million times the mass of the sun. It's about 4 million solar masses. We are heading for a collision with Andromeda. Andromeda has an even bigger black hole in its center. Okay, we're not going to hit it anywhere close. Well, give a few thousand million years, we'll be run into it. Okay, our black holes might miss. They won't get a hit head on anywhere, but they might be close enough to capture each other, spiral around, and then swallow each other up. When that happens, there will be one absolutely stupendous explosion. That explosion will be primarily in the form of gravitational waves. That means ripples in space-time. Those ripples in space-time, if they say took place in here, will make their mark on this crossover surface. You look at the equations, and I have equations for all this. You look at the equations for how this continues to this. They tell you that the information in that gravitational waves will convert into the information in an initial form of dark matter. Now, that's another mystery in cosmology, an accepted mystery. What is this dark matter, which is something like 80% or so of the matter that, more than that actually, a little bit more, of the actual physical matter that we know. There's the other stuff which the dark energy that's actually the cosmological constant in my view, so I'm not going to talk about that. But the dark matter seems to be genuine matter, which is most of the matter around that we have it. Now in this scheme, it has to be created at the crossover. It takes up the gravitational degrees of freedom, you see. The gravitational degrees of freedom, because of this mathematics, it tells you it converts itself into temperature variations or slight velocity variations in the initial form of dark matter. And that we ought to see. Do we see it? That's the question. Now, here's a question. I proposed that you should see this stuff, and I tried to get some people in Princeton to look for it, and they did. They looked at the cosmic microwave background. What would you see? Well, you'd see circles in the sky. You wouldn't actually see that, but you could. Let me give you an image. You imagine a pond, and it's raining, and each drop of water makes a ripple, and that ripple goes out. And at a certain point, you take a photograph of it. Now, that ripple will have got to a certain point. There will be later drops, smaller ripples, earlier drops, bigger ripples. But these ripples will cover the whole of the pond. Now, as you look at that pond, you look like waves all over the place. But if you do clever statistics, you should be able to extract the information that there were individual impacts of the raindrops hidden in these ripples. And that's what these people at Princeton were trying to do. They had a way of trying to look to see whether there was since the black hole encounters are now being the things that I'm talking about, the raindrops falling on the pond, these are hitting it with the black hole explosion, and where the ripple has got to is what you would see. So you see in the sky where the ripple is, and it would be a circle. And so these people in Princeton were trying to look for it, and they looked, as it turned out, a way which probably was the wrong way. They weren't to know that. And then I was a little puzzled about, they claimed they didn't see anything. I thought there was some evidence, but it was due to some subtle thing. And I thought maybe you could see whether there was circles there by twisting the sky. And if you twist the sky, these circles will look like ellipses and not circles. And so the question is, do you still see them if you look at the twisted sky? And they tried that, and there was some evidence of something going on, but it wasn't very persuasive. So I got hold of a friend I'd known for a long time, Vahe Gerzajan, who is an Armenian, and I'd been in communication with him about something rather different, but I knew he'd been looking at things like ellipticities in the sky and so on. And so I asked him, well, is there any evidence, anything you can think of relating to this? And then, not very long after that, I saw him, and he said, well, I've been trying to see whether there's any evidence for these circles, and tell me what you think. And so he showed me this. He'd done it a different way. And if you're doing it that way, maybe you will see not just individual circles, but concentric circles. Now, the reason I said that is because think of a cluster of galaxies. Every now and again, two of them will collide, boom, they have an explosion. Another one will hit it, and you get a black hole, it gets bigger and bigger, it swallows others. And that black hole will emit several times. If the theory is right, it'll go boom, boom, boom. Not like that, of course, it'll be zillions of years between one and the next. But nevertheless, these circles that you look at, it's not so much like raindrops coming from the sky. It's if you've got a corner of the roof, and there are raindrops coming from that corner, and then going blip, 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 blip from that point, and then another corner somewhere else, and they're doing that. Can you see evidence for concentric circles in the sky? Well, he showed me his data, and so I just said, well, look, yeah, since you're doing it that way, do you ever see the same blips somewhere else for the same center? And he looked at me and said, yeah, I do see that. Look at the data. And so I found that quite persuasive. And so we actually wrote a note and sent it up and put it on the archive. And then all sorts of people said, look, you're doing your statistics all completely wrong. This is nonsense. You're doing it wrong because you're not taking into account the power spectrum. Now, I'm not going to tell you what that is. But the thing is, you see, how do you know whether something is a true effect if it's a statistical thing like this? Well, you don't know how many of these circles you ought to see at random anyway. It's a bit difficult to work that out. So how do you do it? Well, what people do is they make a fake sky, a purely made-up sky, and then you see how many circles you see in the fake sky. Do you see as many in the fake sky as in the real sky? Well, that's what he'd done. My colleague, Vahe, had done that. But he hadn't put in the power spectrum. Now, the power spectrum is something that you extract from the data of the microwave background. It's an important thing. And the thing is that he was saying, I shouldn't put it in, because if you put it in, if the circles are really there, putting it in will increase the probability of seeing circles. He said one of these statistical things. And they said, no, you've got to put it in. We all do it that way, and that's the way you have to do it. And so he says, well, no, that's not the way I'm doing it. Well, the arguments went backwards and forwards. And I got rude letters from people saying, you made a perfectly trivial blunder in all this. You should withdraw your paper. Well, the story went on and on. And we actually he now does it. He puts in the power spectrum now. And then it's harder to see. You have to look for multiple circles. We don't have to, because some other people have done it without doing that. But it's harder to see. Effect. Okay, you put the power spectrum in. Okay, yeah, you win. We put it in. We seem to see effects when you look for multiples with the same center. So we put this into a very respectable journal. I'm not telling you what it is. A very, very respectable journal. We put it in. And we said, look, we think this is important. Maybe we could have it rapid publication. They've got a scheme for that. So, all right, yeah, we'll do that. We got some referee comments back. One of them very rude and unhelpful. The two others were helpful. One of them in particular was very helpful. And he made all sorts of useful comments. In fact, he revealed his name, said, I'm so-and-so. If you want to get in touch, that's fine. We'll try and iron out these points. Okay. So we resubmitted, ironing out these points, and said, well, look, we're not so keen on this unhelpful referee who claimed to have done these observations with we don't know how or why or what, getting different answers. I don't want to go into the details of that, but they told me, well, we haven't consulted that referee, that's fine, it's okay. But then, the second time, we got, one person said, fine, very nice paper, that's good. Two other people said, well, we're not so sure about these fake skies you've been doing. Maybe they're not right. Because one of them said, in fact, they seem to disagree with what another referee said. How did they know what another referee said? Because it's supposed to be independent, so we worried about that. Anyway, so my colleague was they said, well, in order to make sure you've done your simulations right, we want to see all the details of your computer code. It's probably time, so I should stop, yes. I should see all your computer codes. So my colleague said, well, that's ridiculous because it's going to take a year to look at them. It's probably right. So then I had this idea of using this twisted sky. So we don't do it that way. We put the twisted sky in. And then this was about several months ago now. And then we come back and got a nice friendly referee, a different one altogether, saying, yes, that's fine. Another referee saying, no, you should put the power spectrum in and do it the old way. I said, no, that's not the point. We're doing it a different way. So then they said, well, that's fine. The editor said, that's fine. We'll take your paper as long as you just make that rather referee happy, explain why he's misunderstood it. So we sent it in. We had to make it shorter, too, and to try and explain why he'd misunderstood. We waited and waited and waited. And then we got three completely different referees, all of them saying we should put in power spectrums and do it in simulations and we shouldn't do it this way. And so this was very strange. So my colleague was too upset by this, and he said, look, I'm going to send it somewhere else. I said, fine. So I said, that's okay, send it somewhere else. 9 days later, we got a letter from this respectable journal that said, we've changed our minds. We've just accepted your paper. Very strange. So I had to say back, well, I'm sorry, we've already sent it somewhere else and got it accepted. It was actually accepted in 9 days. So it's going to appear very soon, but I have to leave you with that. It's a curious story. I have no idea what's been going on behind the scenes. Odd things. Thank you very much.
Thank you very much, Sir Roger. We've got a very few minutes for a few questions, so we just wait for a microphone to reach you before you ask a question. But has anyone got any questions for Sir Roger? None at all. One at the back. There you go. Just wait for
the new journal. Yes. The one is going to appear. It's the European. It's going to appear in the European Physical Journal Plus. And it's been accepted, and it will not be long before it appears.
There's one down here as well. Just wait for a microphone.
How does a universe that keeps starting again reconcile with entropy going up?
Very good question. Yes. No, that's certainly a good question. And I worried about this for quite a while before realizing what the explanation is. The explanation is a bit of a subtle one, and it depends on taking one Stephen Hawking and not the other Stephen Hawking. Now, I should explain that there is an argument that goes on about black holes and information loss. The original argument that Stephen Hawking put was that information was lost in black holes. Now, what it really means, if you look at the definitions of things, it means that I have to say phase space. I hope you're a physicist and I can say phase space, but never mind. What it means The upshot is that you lose degrees of freedom in the black holes. They swallow these degrees of freedom. And that means that your definition of entropy, you have to be jolly careful what you mean by entropy, and that the entropy gets, the zero of it gets replaced. It gets renormalized. You say that the entropy, as soon as that black hole is gone, you say, whoops, no, that means entropy is something else. I should explain that by far the most entropy in the universe now is in black holes, enormously more. Now, when those black holes disappear, as in the whole history of the eon, it'll take something, the biggest black holes will take something like a googol years, 10 to the power 100, one with 100 zeros, years, before they finally disappear. Maybe longer, because there will be some absolutely huge black holes by then. And they will eventually disappear by Hawking evaporation. I'm accepting all that's fine. But what I'm also accepting is the original Hawking statement that information is lost. And what that means is that your entropy definition has to be rescaled. You go into, it's explained in my book. but the information definition, the entropy definition gets changed. It's really because you've lost all the stuff which went into the black hole. And when the universe reaches its maximum expansion, the entropy value has gone down to what it was. But the entropy never, you see, the subtlety is that there is no violation of the second law. It's just you change your mind what you mean by the word entropy. And what you mean by the word entropy gets changed in detail because it depends on the degrees of freedom that you're taking into consideration. When you lose some of those degrees of freedom, that notion of entropy has to be redone, and it goes down. And it does make sense. It's all coherent and consistent. But it's a very good point, and I did worry about that for a long time, and I thought the explanation was a different one for a long time. But I realized this must be it, that it's the information has to be... So you have to take the old Hawking, I'm afraid. The one, I think his original argument was very good, very powerful. I think that the reason that he changed his mind later on, which he did, I think shouldn't have. He was influenced by too many people who told him you should preserve unitarity. It's the unitarity. You see, it's connected with the puzzle I have with the faith issue. That quantum mechanics would demand that unitarity is always true, and that means you can't lose information. But I'm saying that that's not true. At a certain level, when gravity gets involved, that rule that demands that Schrödinger's cat's alive and dead at the same time, if you like, that rule has to be wrong. And that it's shown to be wrong in the Hawking process, but because you lose information. Sorry, I was taking
couple more questions.
There are a couple more questions.
There's three. We'll just say there's three. One there, and then one.
Okay.
There. Yep. Do you want to just wait for the mic? Yep.
You spoke about the universe. Obviously, it's expanding at an accelerating rate, and you get this stage where the universe becomes incredibly rarefied.
Yep.
You propose the existence of this anti-Higgs mechanism, so to speak. By what mechanism that allow the universe to recondense and then to re-expand again?
Well, it doesn't actually compress. It loses track of its scale. No, the mechanism is you just have to have equations which govern it. I mean, the picture I have, I'm like trying to visualize what happens. Suppose you built some compartment, you see, which was immune to all this, and it's very good thick walls, and you just sit there and wait what happens. Well, that would be all right, except that because of this inverse Higgs mechanism, eventually that material will evaporate away, and it just becomes radiation. You can't do it. I mean, it'll take a lot longer than the 10 to the 100 years that the black holes take to disappear, much, much longer than that. And then these things will just become radiation. And then there's no scale for them. They're big and small at the same time. But you do need equations to tell you how to control that. And that's completely right. So you need to have a set of equations which makes it all deterministic. There are things like saying your conformal factor has to turn into its inverse, and it does that. It's done in the appendix to my book, Cycles of Time, but not very well. I think it's probably better in this article, which I had to put an appendix in the article, which will be coming in the European Physical Journal, and I think that's clearer. There are some uncertainties about the equations too. Exactly how to do it absolutely clear. But it looks like a pretty consistent scheme.
There was one just behind as well, and then in the corner.
I know that at the moment many physicists are interested in developing techniques to observe gravitational waves. So I was wondering, have you thought about new ways to test your theory once we become able to observe these waves?
Gravitational lensing, you say?
Oh, gravitational waves.
Gravitational waves? Well, it would to some degree, because, for example, inflationary theory, this is one of the tests, whether you will have any indication of primordial gravitational waves. So is there any indication in the very early universe that there were gravitational degrees of freedom? And I believe it's the case that, at least, I think it's not all theories of inflation, but most inflation theories will predict there should be this gravitational radiation. This scheme, I think there shouldn't be, because it really does kill off the gravitational degrees of freedom. It's built into the whole way the scheme works, the way the conformal factor works, that it just kills the gravitational degrees of freedom. Stone dead wouldn't be quite correct. First of all, it converts it into motions of the dark matter in the initial form, and that's what you would see. The rings that I'm saying you're supposed to see in the sky are due to a kick. The gravitational wave gives it a kick, and in our eon, that kick becomes a motion of dark matter. And so you see it slightly warmer when it's coming towards you, and slightly cooler when it's going away from us. But it's a sort of negative thing that, according to the scheme, you would not see, I think, any evidence of primordial gravitational radiation. So, yes, that is a test.
Thanks.
And then last one in the corner, please.
You said in one of your books that cosmology is becoming an exact science because there's so much data available. But you've been telling us this evening also about all the uncertainties over the nature of the universe and entropy.
Yes.
So how much of cosmology is firmly based on observational evidence and how much is just conjecture?
Well, it's less conjecture than it used to be. I mean, there is an awful lot of conjecture. And if I might say, when I talk about fantasy and so on, a lot of the implications of inflation. Now, inflation, there are different forms of it, but the thing which is called eternal inflation requires that you have little different universe things, and they bubbles, and they run into each other, and so on. And so, to me, there's a lot of fantasy in that, you see. But then, you see, I'm open to people criticizing my scheme, saying, isn't that fantasy? But then I'm saying that there are observational aspects to this scheme, and that is what makes it not fantasy. Now, the question is whether these signals which I'm claiming are there are actually there, or are they really some statistical artifact, which is, as far as I can see, pretty difficult to mock up what we seem to be seeing there. But, of course, that's for other people to claim. But I think that cosmology encompasses a lot of things. There is that part of cosmology which involves these bubbles and these eternal inflation and Boltzmann brains and goodness things. And to my mind, there is a lot of incredible amount of speculation there, which the microwave background is hardly related to, I think. But the microwave background does give you an awful lot of detailed information about things which was not there before. I think it does make a big difference. And in particular, the signals which I'm claiming should be there from this scheme of mine should be in the microwave background. And with the Planck, the data that we looked at comes from the old WMAP data. There is this newer satellite, the Planck satellite, but the data from that has not been released yet. So people aren't allowed to look from my circles in that data. But we are not allowed to because we don't have the data. Other people aren't allowed to because it's decreed what they're supposed to look at. So it's a bit funny. But sometime later, I don't know, in a few months' time, it's supposed to become available. And then there will be a lot more data than there has been up to this point, and people can test their theories against that data. And I think if they can't test it against the data, then it's surely, yes, it is a lot of speculation. But it's those theories which do have something to say about the microwave background are theories which, maybe there are other things you could test too, but those are certainly ways in which your theories could become proper science and not just speculation.
Thank you. So Roger will be signing a few books outside afterwards, but first can we just say a huge thank you for coming and giving such a fascinating talk, Sir Roger.
Thank you.
Thank you. Okay. Just have a